Hi everybody, today's lecture is entitled Hardy-Weinberg Equilibrium. So basically, so far we've been talking about the different evolutionary forces that act on a population. The question we need to now ask is, how do we know if any of these evolutionary forces are in fact acting on a population? The way we do this is by measuring the allele frequencies for specific traits. In particular, we're going to be comparing the observed frequencies to the expected frequencies for specific traits, and these observed and expected frequencies are going to be predicted by a mathematical model called the Hardy-Weinberg equilibrium model, and we compare the observed and the expected using a test known as the chi-square test. Once again, this mathematical model is called the Hardy-Weinberg equilibrium model. Hardy-Weinberg equilibrium basically provides a baseline set of evolutionary expectations assuming specific conditions where no evolution occurs. So we're envisioning a situation where no evolution is occurring. Hardy-Weinberg equilibrium will be in effect. The Hardy-Weinberg equilibrium model assumes that no evolutionary forces are occurring. That is, there's no natural selection, there's no mutation, there's no migration, there's no gene flow, there's no non-random mating. So what this means is that all the genes in the population have equal chances of recombining in each generation. So once again, the assumptions of Hardy-Weinberg is that there's no mutation, that there are no new alleles that are going to be added by any molecular alterations. There's going to be no migration. There's no new alleles added by the movement of individuals. There will be no natural selection. All the alleles in the population have equal fitness. There's random mating. There's going to be no bias in mating. Short people are just as likely to mate with a tall person as a tall person is equally likely to mate with a short person. The population is also predicted to be very large, and this is very important in terms of genetic drift because there'll be no sampling error, and if there's no sampling error, there'll be no genetic drift. With Hardy-Weinberg, the allele frequencies are related to Mendelian genotype proportions. And this is a very basic extension of the simple Mendelian genetics that we've been talking about so far. This mathematical relationship of the allele and the genotype frequencies in population is called the Hardy-Weinberg formula or law. The simplest application of Hardy-Weinberg equilibrium to microevolutionary study involves a genetic trait that follows a very simple Mendelian pattern and has two alleles, the A allele and the B allele. The frequency of the dominant allele, in this case we'll say A is the dominant allele, equals P. The frequency of the recessive allele, in this case we'll say B is the recessive allele, and it equals Q. P plus Q, the frequency of the dominant allele plus the frequency of the recessive allele, will always equal 1. Remember, frequency equals the proportion of the population, and it always ranges from 0 to 1. To determine the expected proportion of genotypes, the first thing we do is we compute the chances of all possible allele combinations. So we calculate the proportion of the chance of all possible allele combination. What's the chance that A combines with B? These probabilities are a function of the frequency of the two alleles. The frequency that A is going to combine with B is the frequency of A and the frequency of B. The quantity is always going to be squared because there are two chromosomes, one from each parent. You're going to get two alleles from mom, or you can get one allele from mom and one allele from dad. But every individual has two alleles of each trait. So the Hardy-Weinberg formula is P plus Q times P plus Q equals 1. We do something known as the binomial expansion. In all honesty, for this class, you don't need to know the mathematics behind the binomial expansion. But let me just show you a little bit. P squared. P equals A, and we said that before. The frequency of A equals P. For people with the homozygous dominant genotype AA, they have two P alleles. P times P equals P squared. For people with the heterozygous genotype, there are two forms of the heterozygous genotype. You could have dominant A and recessive A, or you could have recessive A and dominant A. This is the equivalent of P times Q plus Q times P. Calculated out algebraically, it would equal 2PQ. The frequency of the two recessive alleles, AA, little a, equals QQ. Equals, or Q times Q, which equals Q squared. Once again, you don't need to know the binomial expansion per se, but you do need to know that the homozygous dominant genotype equals P squared, the heterozygous genotype equals 2PQ, and the homozygous recessive genotype equals Q squared. So how do we then tell if a population is in fact in equilibrium? There are three steps. First, we figure out the allele frequencies of the population. This is known as the gene counting method. And basically what we're doing is counting the alleles, the frequency of each of the alleles. Then we calculate the expected frequencies of the population. When we calculate the allele frequencies of your population, this is the observed frequencies. In step 2, what we're doing is calculating the expected frequencies of the population. This is effectively using the Hardy-Weinberg equilibrium formula to calculate the expected frequencies. We then compare the observed and the expected values, and this often involves a chi-square test. Let's look at example 1. We're going to use the allele frequency calculation, commonly called the gene counting method. Let's say the population has 3 genotypes: homozygous A, heterozygous, and homozygous B. So homozygous A is the dominant, homozygous B is the recessive. We know the proportions of each genotype within the population. We have 15% of the population has homozygous dominant, 60% of the population is heterozygous, and 25% is homozygous recessive. Excuse me. The A frequency, or the A allele, is found in both the homozygous and in the heterozygous individuals. In the homozygous individuals, they each have 2 dominant A alleles. In the heterozygous individuals, they have 1 A allele per individual. So to calculate the frequency of the A alleles within the population, we need to calculate the frequency in the homozygous A, homozygous dominant, as well as the proportion of A alleles in the heterozygous individuals. We do it in the following manner. A equals 2 times 0.15 Y2, because the individuals with the homozygous dominant genotype have 2 A alleles, so 2 times 0.15 plus 1 times 0.6, which is the frequency of the heterozygous, and they only have 1 A. And then we divide it by 2. So 2 times 0.15 is 0.30, plus 1 times 0.6 is 0.6. This adds up to 0.9 divided by 2 equals 0.45. So the frequency of the dominant allele, or A, or P in this example, is 0.45. The 2 can be distributed like this: 0.15 plus 1/2 times 0.6 equals 0.5 equals P. So you can calculate it in a variety of ways and still get the correct answer. So P is the proportion of A alleles, and that equals 0.45. Now we need to find Q, the proportion of B alleles. B is found once again in the homozygous B individuals, or the homozygous recessive individuals. Homozygous recessive individuals each have 2 B alleles per individual. And we also have the B alleles in the heterozygous individuals, but they only have 1 B allele per individual. We calculate it in the same manner we did for the A. 2 times 0.25, so we have, for the homozygous recessive Bs, we have their frequency is, the proportion of B alleles is 0.25, so 2 times 0.25 plus 1 times 0.6. This is 50 plus 0.6 is 1.1. 1.1 divided by 2 equals 0.55. A second method of doing it is 0.25 plus 1/2 of 0.6 equals 0.55. So note that Q equals 0.55, or the frequency of B equals 0.55 in this population. So now that we know that P is 0.45 and Q is 0.55, now we need to find that represents the observed genotype frequencies. Now we need to calculate the expected genotype frequencies. That is the genotype frequencies we would expect if the population was not evolving. If the population is in Hardy-Weinberg, what are the expected genotype frequencies? The first thing we do is we write out our Hardy-Weinberg equilibrium formula. P squared plus 2PQ plus Q squared equals 1. P squared, remember, equals the frequency of the homozygous dominant genotype, which in this example is AA. We know that the frequency of A equals 0.45, so we say 0.45 times 0.45, because it's P squared, equals 0.2025. The frequency of the heterozygote is 2PQ, which in this case, our example is AB genotype. So 2 times 0.45 times 0.55 equals 0.495. And Q squared is the frequency of the expected frequency of the homozygous recessive genotype. In our example, that would be BB. So 0.55 times 0.55 equals 0.3025. You add these up, and they nicely add up to 1. So these are, once again, your expected genotype frequencies. The next step is we need to compare the actual observed genotype frequencies to those predicted by the Hardy-Weinberg equilibrium formula. If they are similar, evolution is not occurring. If they are different, evolution is occurring. So then we put in our observed frequencies. The frequency of the homozygous dominants is 0.15. The frequency of the heterozygotes is 0.6, and the frequency of the homozygous recessives is 0.25. Now we put in our expected frequencies that we just calculated using Hardy-Weinberg. Frequency of the homozygous dominant should be 0.2025. The frequency of the heterozygote should be 0.495, and the frequency of the homozygous recessive should be 0.3025. Notice that there are some differences. Okay, so we can tentatively say evolution is occurring, but we actually need to test statistically whether those differences are of a statistically different nature. How different is it? Okay. But for now, we're just going to accept that they are in fact different. Example 2, let's look at a second example. We're going to look at the MN blood type, and these are calculate the observed frequencies. We have 3 genotypes: MM, homozygous dominant; MN, heterozygous; and N, homozygous recessive. There are going to be 100 individuals total in this population. 4 have the homozygous dominant genotype, 40 have the homozygous dominant genotype, 40 have the heterozygous genotype, 20 have the homozygous recessive genotype. We now calculate the number of alleles, the number of M alleles, and the number of N alleles. You could actually think of this as the number of P alleles and the number of Q alleles. The number of M alleles for the 40 individuals that have the homozygous recessive genotype would be 80. This is because they have 2 M alleles. So 40 times 2 equals 80. The frequency of M alleles for the heterozygotes is only 40 because they only have 1 M allele. The frequency of M alleles for the homozygous recessive genotype is 0 because this is NN. There are no M alleles. We now calculate the N alleles, or the Q. The frequency for the homozygous dominant, MM, is 0 because there are no N alleles. The frequency of the N alleles for the heterozygote is 40. And the frequency of the N alleles for the homozygous recessive genotype is 20 times 2, which equals 40. We calculate the total number of M alleles. 80 plus 40 equals 120. The total number of N alleles, 0 plus 40 plus 40 equals 80. Notice we now have 120 120 plus 80 alleles, totaling 200 alleles. This is twice the number of individuals because each individual has 2 alleles. We calculate the observed frequencies for each allele type. P, or in this case M, equals 120 total number of M alleles divided by 200, the total number of alleles in the population. 120 divided by 200 equals 0.6. Q, or in this case N, equals the total number of the recessive alleles. 80, which is the total number of N alleles, divided by 200, the total number of alleles in the population, equals 0.4. 0.6 and 0.4 equal 1. These are the observed frequencies of the M and N alleles in the population. Now we calculate the expected frequency for the genotypes. We have MM and MN and NN. These are the 3 genotypes. We then use our Hardy-Weinberg equilibrium formula. The homozygous dominant is P squared, the heterozygote 2PQ, the homozygous recessive Q squared. We said that the frequency of the M allele is 0.6, so 0.6 times 0.6 equals P squared, so the expected frequency equals 0.36. 0.6 times 0.6 equals 0.36. For the heterozygote, we said it should equal 2PQ, 2 times P, which equals 0.6, which times Q, which equals 0.4. 2 times 0.6 times 0.4 equals 0.48. Sorry, I didn't mean to go forward. So 0.48 equals the expected frequency of the heterozygote, and then NN equals, or the homozygous recessive, equals Q squared. We said the frequency of N equals 0.4, so 0.4 times 0.4 equals 0.16. So notice that these frequencies all add up to 100. 7, 8, 12, yes they do, just double checking. Okay, so these are now your expected frequencies. Now we compare the observed and the expected frequencies using a chi-square test. Remember I said before we just accepted that they were different. Now we're actually going to test whether the observed and the expected are in fact different. So these are your observed. If we have 40 homozygous dominant, 40 heterozygous, 20 homozygous recessive. The expected would be 36, 48, 16. So we see that they're different. How different are they? Well, we calculate their difference. 40 minus 36 is 4. 40 minus 48 is negative 8. 20 minus 16 is 4. We do a test called the chi-square test. We calculate the observed minus the expected. So 40 minus the expected equals this difference right here. We then take this value and we square it. So 4 times 4, negative 8 times 8, negative 8 times negative 8, 4 times 4. So 4 times 4 is 16. Negative 8 times negative 8 equals 64. 4 times 4 equals 16. We then divide that value by the expected frequency. So the expected frequency would be 36, 48, 16. So 16 divided by 36 is 0.44. 64 divided by 48 is 1.33. 16 divided by 16 equals 1. We sum these values and it gives you 2.77. This is your summed frequency. The sum of the value for the chi-square test. So your chi-square, this value right here, the x squared, will equal 2.77. Tells you effectively how different the observed and the expecteds are. We then read this value using what's called a probability table. The chi-square test is 2.77, and we have what we call 2 degrees of freedom. This means that our p-value, the likelihood that this result would happen by chance, is between 0.20 and 0.30. Okay, right here. It would be right here, 2.77. The results are only considered statistically significant if the result would be 5.99 or greater. Okay, so we would say that even though the values are different, there's insufficient evidence to reject the null hypothesis that there's no difference. So we would say there is no significant statistical difference between observed and expected. We'd only see the difference 25% of the time, and that's not statistically very likely. Okay, it has to be much greater for us to say that the difference is statistical. So let's think about what those results mean. Even though they're not statistically significant, what do they mean? Well, one of the things that we can see is that there are in fact more homozygotes than expected in that population. It could mean that there is an evolutionary force acting on the population even though it's not statistically significant. The match isn't perfect, but it's close enough to satisfy equilibrium conditions statistically. We would still say the population is not evolving, and it is, in fact, in equilibrium. A corollary of this is the genotype frequency calculation. If you know the allele frequencies of a population when they are at equilibrium, it's possible to calculate the genotype frequencies. This is the same thing we do to find the expected genotype frequencies when we don't know that the population is in fact in equilibrium. The frequency of the homozygotes equals the allele 1 or 2 frequency squared. The frequency of the heterozygotes equals 2 times the allele 1 frequency times the allele 2 frequency. The frequency of the C allele equals 0.4, so the frequency of the homozygous CC genotype equals 0.4 squared, in this case 0.16. Let's say the frequency of the D allele equals 0.6, so the frequency of the homozygous double D genotype equals 0.6 squared or equals 0.36. The frequency of the heterozygous genotype CD, 2 times 0.4 times 0.6 equals 0.48. A shortcut for calculating some of these frequencies is we determine if only the homozygote frequencies are equal to p squared and q squared. We test for equilibrium by taking the square roots of the homozygote frequencies and adding them up. If the result equals 1, the population is in equilibrium. The square root of 0.16 equals 0.4. The square root of 0.36 equals 0.6. 0.4 plus 0.6 equals 1, so the population is in fact in equilibrium. There's also what's called the square root method. Can also be used to determine allele frequencies for traits where there is in fact dominance. It's not easy to see all the genotypes when there is dominance. When there's dominance, it's very difficult to use the gene counting method. So just keep in mind the fact that you want to use your square root method when there's dominance. Let's take an example of a trait called PTC. PTC is a chemical that can be tasted. It's an autosomal dominant trait. 96% of the U.S. population is capable of tasting PTC. 4% of the population can't taste PTC. So how do we calculate gene frequencies? 96% of the tasters constitute both the homozygous dominant genotype frequencies as well as the heterozygote genotype frequencies, so the p squared plus the 2pq. Because it's a dominant trait, you only need one allele to actually taste it. The non-tasters, the 4% of the population, are the homozygous recessive genotypes. With PTC tasting, so the TT, two little t's, the homozygous recessive, equals the frequency of t squared, recessive t squared. The frequency of t will then be, of little t, equals the square root. So the square root of 4%, which is 0.04. So the frequency of t, the square root of 0.04 equals 0.2. So the frequency of the recessive t equals 0.2. If the frequency of the recessive T equals 0.2, the frequency of the dominant T has to be 0.8 because P plus Q always equals 1. Another example with Rh blood type. Our population only has 2 alleles. You can be positive or negative. 25% of the population has negative blood types, the genotype negative. 75% have positive blood types. And once again, the positive blood types can be plus or can be a heterozygote plus minus. The frequency of the negative allele equals the square root of 0.25. The square root of 0.25 is 0.5. Consequently, the frequency of the positive allele is 1 minus 0.5, which is 0.5. Okay. The square root method and the genotype frequency calculation. We can also use Hardy-Weinberg to determine genotype frequencies. Plus is the equivalent of P squared because it's homozygous dominant. So that would be 0.5 squared equals 0.25. The heterozygote plus minus equals 2PQ, which equals 2 times 0.5 times 0.5, which equals 0.5. And the negative was the homozygous recessive, which equals Q squared. So 0.5 squared equals 0.25. So whenever we have 3 identifiable genotypes, use the gene counting method. It will always give you the correct gene frequencies. The square root method and genotype frequency calculation. If we use the square root method and the population is not in equilibrium, I want to make it clear you're not going to obtain correct allele frequencies. Let's take an example. Let's say the frequency of the homozygous dominant is 0.25. The frequency of the heterozygote is 0.39, and the frequency of the homozygous recessive is 0.36. They add up to 1. Using the square root of 0.25, we get 0.5. The square root of 0.36 equals 0.6. 0.5 plus 0.6 equals 1.1. So you know the population is not in equilibrium, and you know that you shouldn't be using the square root method. Let's take another real-world example. There's a chemical called phenylketonuria, PKU. 1 in 40,000 children are born with this metabolic abnormality in Europe. If you look at any bottle of Coca-Cola or something, it specifically states phenylketonuria, people who are sensitive to it shouldn't be drinking Coca-Cola. It's an autosomal recessive condition. That means that only individuals who are homozygous recessive for the condition exhibit it. The relative frequency, as I said, is 1 in 40,000. If you calculate it out to the decimal, it's 0.000025. So the frequency of Q squared equals 0.00025 squared. And so, or times itself. This times itself would be substantial. I'm sorry, this is Q squared. So the frequency of Q squared, this is the frequency of Q squared. If we want to figure out the frequency of Q, we take the square root of this value. The square root of this value equals 0.005. This means that 0.5% of the gene pool is K, little k, recessive K, while 99.5% of the population is normal allele dominant K. The probability of being a carrier with for PKU is the equivalent of 2PQ. 2PQ equals 0.01. How do I calculate that? 2 times 0.995, this is the frequency of P, times 0.005, the frequency of Q. This means that approximately 1% of the population are carriers. 1 out of 100 individuals are going to be carriers for PKU. So what's the probability that 2 people will have a child with PKU? The probability of two people being carriers for PKU is 0.01 times 0.01, which equals 0.0001. If both are carriers, that means 1/4 of the children are expected to have this defect. We multiply 0.001, the probability both parents are carriers, by 0.25, the probability that they're going to have a PKU child, because it's a 1 in 4 chance. Then the probability that any random couple will have a child with PKU is 1 in 40,000. So that's how we've calculated out what the probability is. Populations in general contain large reservoirs of deleterious alleles in heterozygous condition. Each individual has 3 to 5 alleles that are in a homozygous condition that, if they were in a homozygous condition, would lead to death or disablement. The genetic load is the totality of deleterious alleles in a population. So most individuals have 3 to 5 alleles that are really, really bad. You multiply that by the total number of those alleles in the population, and that constitutes the genetic load in the population. The evolutionary factors that we've been discussing, mutation, migration, genetic drift, natural selection, non-random mating, they all interact to produce variation and to distribute genes within and between populations. But there's no long-term direction to any of these factors. So how do these populations adapt? How do they have direction? A result of natural selection is a change in allele frequency relative to specific environmental factors. If the environment changes, then the selective pressures change. Such a functional shift in allele frequencies is called adaptation. The best documented case of natural selection in humans deals with sickle cell trait, which I discussed previously.